In the previous section, we learned how to define a sample space and calculate the probability of simple and compound events. Next, we look at how events interact with one another, and this is where we introduce the crucial concepts of marginal and joint probabilities. These concepts are often best visualized using a contingency table, which allows us to analyze two variables simultaneously. Let's start with marginal probability. This is the probability of the occurrence of a single event without consideration of any other event. It's also often called as simple probability. It gets its name because these probabilities are calculated in the margins of the table. You simply divide the corresponding total for a single row or a single column by the grand total. Next, we have joint probability. This is the probability that two events will occur simultaneously. It is also known as the probability of the intersection of events, and is written as this or this. Think of an intersection area in the Venn diagram again. Okay, so that represents the probability of two events happen at the same time. So the probability of the events occurring, such as selecting a student who is both male and an engineering major, is a joint probability. This number lives inside the main body of the contingency table. This table summarizes the difference. Let's look at the notation A1 and A2 are outcomes for one variable, and B1 and B2 for another. The values inside the table, like B over N here, is joint probability, where the probability of A2 and B1 occurring together. We would read this as the joint probability of A2 and B1. The totals in the right and bottom margins are marginal probabilities, representing the chance of a single event, A1, regardless of B's outcome. Now for one of the most practical concepts in probability, that is conditional probability. This probability is the probability that an event will occur given that another event has already occurred. We write this as the probability of event will occur given that another event has already occurred. We write this as here. So this vertical line means given that, or on the condition that. So the probability of event A given event B has happened is given here, and vice versa, the probability of event B given event A is this. This formula connects the ideas of joint and marginal probability. The theorem states that the conditional probability of B given A is the ratio of joint probability of A and B to the probability of the given event, provided the probability of event A is not zero. So essentially, when we condition on event A becomes our new reduced sample space, and we look at the part of the intersection within that new space. As we just discussed, conditional probability is typically used to find the law of an event given that this law is used when the sample space S given that one of its possible causes of mutually exclusive theorem, however, does the reverse. B1, we use it to find the probability of the possible cause. So the law states that the probability of any event A, so this is the form event A, is the sum of the probability. This theorem is essential because it allows us to update our beliefs to refine the probability of a cause based on new evidence. This is essentially the marginal statistical inference and is widely used in real contribution scenarios. So you now possess the fundamental probabilistic theorem. The foundation of this analyze uncertainty and total probability data-driven. This law is used when the sample space S is partitioned into a set of mutually as we just discussed, conditional probability is typically used to find the probability of an event given that one of its possible causes has occurred. Bayes' theorem, however, does the reverse. We use it to find the probability of the possible cause given that the event has occurred. So this is the formula here. This theorem is essential because it allows us to update our beliefs to refine the probability of a cause based on new evidence. It is a cornerstone of statistical inference and is widely used in real-world prediction models. So you now possess the fundamental probabilistic toolkit necessary to analyze uncertainty and make informed data-driven decisions, which concludes our module on probability based on frequency.